Tonight, we're going to explore something that might genuinely unsettle you. The moon, that familiar companion that has hung in our sky since before humans existed, is leaving us. Not metaphorically, literally. Every single year, the moon drifts a little farther away from Earth. And this isn't some wild theory or speculation. We've measured it with lasers bounced off mirrors that astronauts left on the lunar surface. The moon is abandoning Earth at a rate we can calculate down to the millimeter. But here's what makes this truly fascinating. This slow departure is connected to something you experience every single day: the tides. And by the end of this journey, you're going to understand exactly why the moon is leaving, what it means for Earth's future, and why this cosmic breakup has been happening for billions of years. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something remarkable. We know with extraordinary precision exactly how fast the moon is moving away from Earth. This is not guesswork. This is not estimation. This is not some theoretical calculation based on assumptions and models. This is direct measurement, so accurate that we can track the moon's distance to within a few millimeters. Think about that for a moment. The moon is about 384,400 kilometers away on average. That is roughly the distance you would travel if you drove around Earth's equator 9.5 times. And yet, we can measure changes in that distance smaller than the width of your fingernail. We can detect movements so tiny that they would be invisible under a magnifying glass. This level of precision seems almost impossible when you consider the vast gulf of space that separates Earth from the moon. How can we possibly measure something nearly 400,000 kilometers away to an accuracy of millimeters? The answer begins with one of humanity's greatest achievements: the Apollo missions. When Neil Armstrong and Buzz Aldrin walked on the moon in July of 1969, they did not just plant a flag and collect rocks. They did not simply take photographs and leave footprints. They left something behind that would revolutionize our understanding of the Earth-Moon system for generations to come. Among the scientific instruments deployed on the lunar surface was a device called a retroreflector array. It sounds complicated, but the concept is beautifully simple. A retroreflector is a special kind of mirror that bounces light directly back toward its source, no matter what angle the light comes from. If you shine a flashlight at a retroreflector from any direction, the light will return straight back to you. Corner cube reflectors, as they are technically called, use 3 mutually perpendicular mirrors arranged like the corner of a cube. Imagine looking into the corner of a room where 2 walls meet the floor. That corner, if it were made of mirrors, would bounce light back exactly the way it came. When light enters this arrangement, it bounces off all 3 surfaces and returns precisely along its original path. This is different from an ordinary flat mirror, which only reflects light back to its source if you shine the light straight at it. A retroreflector works from any angle, which is crucial when you're trying to hit a target nearly 400,000 kilometers away. The Apollo 11 astronauts placed a panel containing 100 of these corner cube reflectors on the lunar surface in the Sea of Tranquility. It is still there today, sitting on the moon, waiting patiently to reflect laser beams back to Earth. The panel is about the size of a large suitcase, and it has been sitting on the lunar surface for more than 50 years now. It requires no power. It has no moving parts. It simply sits there, doing its job, decade after decade. But Apollo 11 was not the only mission to leave retroreflectors on the moon. Apollo 14, which landed in February of 1971, deployed another array. Apollo 15, which landed in July of 1971, deployed the largest array of all, containing 300 corner cube reflectors. These 3 American missions placed retroreflectors at 3 different locations on the moon's near side, giving scientists multiple targets to aim at. And the Americans were not alone. 2 Soviet robotic missions also contributed to this scientific endeavor. Luna 17, which landed in November of 1970, and Luna 21, which landed in January of 1973, both carried French-built retroreflector arrays. These were smaller than the American arrays, but they added 2 more targets onto the lunar surface. Today, there are 5 retroreflector arrays on the moon's surface, all still functioning perfectly after more than 50 years of exposure to the harsh lunar environment. They have survived temperature swings from about 130 degrees Celsius during the lunar day to minus 170 degrees during the lunar night. They have endured constant bombardment by cosmic radiation and micrometeorites. And yet, they continue to work exactly as designed. They are among the longest-lasting scientific instruments ever deployed by humans. Here is how the measurement works. Scientists on Earth fire extremely powerful laser pulses at the moon. These are not ordinary lasers like the pointer you might use in a presentation. These are high-powered research lasers capable of producing brief, intense pulses of light. The lasers are aimed with extraordinary precision at the known locations of the retroreflector arrays. Even with the best aiming systems, hitting a target the size of a suitcase from nearly 400,000 kilometers away is extraordinarily difficult. The laser beam spreads out as it travels through Earth's atmosphere and across space. By the time the beam reaches the moon, it has expanded to cover several kilometers of the lunar surface. Only a tiny fraction of the photons in that expanded beam actually hit the retroreflector array. Most of the light misses entirely, striking the surrounding lunar soil, which absorbs it or scatters it in random directions. But the photons that do hit the reflector bounce straight back toward Earth. They retrace the path they took from Earth, traveling back through space and through the atmosphere to the telescope that sent them. By the time these reflected photons return to Earth, the signal has weakened enormously. The beam has spread out both on the way to the moon and on the way back. The retroreflector itself only captures and reflects a tiny fraction of the incident light. Out of the roughly 300 million billion photons in a typical laser pulse aimed at the moon, only about 1 photon per second, on average, makes it back to the telescope. Sometimes researchers wait for many pulses before detecting a single returned photon. This is why lunar laser ranging requires some of the most powerful lasers and most sensitive detectors on Earth. The McDonald Observatory in Texas was one of the first facilities to conduct these measurements, beginning almost immediately after Apollo 11 returned. The Observatoire de la Côte d'Azur in France has been making lunar laser ranging measurements since 1984. The Apache Point Observatory in New Mexico operates one of the most precise lunar laser ranging systems in the world, capable of achieving millimeter-level accuracy. Each session involves firing thousands of laser pulses and carefully counting the rare photons that return. The key measurement is time. When scientists fire a laser pulse at the moon, they record the exact moment of firing using atomic clocks accurate to billionths of a second. Then they wait. The light travels to the moon, bounces off the retroreflector, and returns to Earth. When the detector registers a returned photon, the arrival time is recorded with the same extreme precision. The difference between these two times is the round-trip travel time. Light travels at about 299,792 kilometers per second. This is the speed of light in a vacuum, one of the fundamental constants of physics. It is the same everywhere in the universe, and it never changes. The round trip to the moon and back takes roughly 2.5 seconds. By timing this journey with atomic clocks and dividing by 2, scientists can calculate the one-way distance to the moon. The precision achieved is astounding. Early measurements in the 1970s determined the Earth-Moon distance to within about 15 centimeters. That was already remarkable, measuring a distance of nearly 400,000 kilometers to an accuracy of 15 centimeters. But technology has improved dramatically since then. Today, the best measurements achieve precision of about 1 millimeter. That is measuring a distance of nearly 400,000 kilometers to an accuracy of 1 millimeter. It is like measuring the distance from New York to Los Angeles and being accurate to within the thickness of a human hair. This technique is called lunar laser ranging, and it has been conducted continuously since 1969. Over more than 5 decades, scientists have accumulated an enormous data set of precise distance measurements. Thousands upon thousands of individual measurements, taken from multiple observatories, using different equipment at different times of day and different seasons of the year. This wealth of data allows scientists to separate the signal from the noise, to identify systematic errors, and to extract the true behavior of the moon's orbit with extraordinary accuracy. And this dataset reveals something profound. The moon is moving away from Earth at an average rate of about 3.8 centimeters per year. Let me put that in perspective. 3.8 centimeters is about 1.5 inches. It is roughly the width of a golf ball. It is the length of your thumb from the first knuckle to the tip. Every year, the moon drifts that much farther away from us. It does not sound like much, does it? At that rate, it would take about 26 years for the moon to move 1 meter farther away. It would take about 26,000 years to move 1 kilometer. In a human lifetime, the moon moves only about 3 meters farther from Earth. You could never perceive such a small change. The moon tonight looks identical to the moon your grandparents saw. Identical to the moon that shone on ancient civilizations. Identical, for all practical purposes, to the moon that has illuminated Earth's nights for millions of years. But here's where scale matters. The moon has been receding from Earth for billions of years. Not millions, billions. Even at this seemingly slow rate, the cumulative effect is enormous. Over the 4.5 billion years since the moon formed, it has moved from being extremely close to Earth to its current distance of 384,000 kilometers. The moon's orbit has been expanding for as long as the moon has existed. Every day, every year, every century, every million years, the moon has been slowly, steadily, inexorably moving away. The lunar laser ranging experiments do not just measure distance, they reveal subtle variations in the moon's orbit. The moon's distance from Earth is not constant even over short periods. It varies throughout each month as the moon follows its slightly elliptical orbit. At its closest point, called perigee, the moon is about 356,500 kilometers away. At its farthest point, called apogee, It is about 406,700 kilometers away. That is a difference of about 50,000 kilometers, or roughly 13% of the average distance. The laser ranging data shows all of these variations with exquisite precision. Scientists can track the moon's position so accurately that they can detect the gravitational influence of individual asteroids passing through the inner solar system. They can measure how the moon's orbit is affected by the gravity of the Sun, Jupiter, and the other planets. They can even detect tiny wobbles in the moon's rotation caused by its slightly asymmetric mass distribution. But the most significant long-term trend in all this data is the steady increase in the moon's orbital distance. Year after year, decade after decade, the measurements confirm that the moon is slowly spiraling outward. This recession has been measured with such consistency and precision that it is one of the most well-established facts in astronomy. Different research groups using different equipment at different observatories all get the same answer. The moon is receding at 3.8 centimeters per year. Now, you might wonder why the moon is moving away. What force could possibly be pushing our cosmic companion farther from us? The answer might surprise you. It is not some mysterious cosmic force. It is not radiation pressure from the sun. It is not the gravitational influence of other planets tugging the moon outward. The force that is pushing the moon away is something you experience twice every day if you live near the ocean. It is the tides. The same tides that fishermen check before heading out to sea, the same tides that beachgoers watch to know when to swim, the same tides that have shaped coastlines for billions of years. Those tides are the mechanism driving the moon's slow departure. But before we explore the physics of how tides can move something as massive as the moon, let's appreciate just how remarkable the Lunar Laser Ranging Program really is. It represents one of the finest achievements of precision measurement in all of science. When you fire a laser at the moon, the beam does not stay tightly focused. It spreads out due to diffraction, the natural tendency of light waves to expand as they travel. It spreads further due to turbulence in Earth's atmosphere, the same effect that makes stars twinkle. By the time the laser reaches the moon, the beam has expanded to cover several kilometers of the lunar surface. The retroreflector array, which is only about half a meter across, intercepts only a tiny fraction of this spread out beam, and then the reflected photons have to travel all the way back to Earth. They spread out again as they cross the vast distance between Moon and Earth. By the time they return, the signal has weakened to almost nothing. The vast majority of the photons that left the telescope are lost. They miss the reflector, or they scatter in the wrong direction, or they are absorbed by the atmosphere on the way back. Only a handful make it through. Detecting these rare returning photons requires extraordinary sensitivity. The detectors used for lunar laser ranging can register individual photons, single particles of light. They can distinguish the faint returning signal from the background noise of scattered moonlight and starlight. They can time the arrival of each photon to within picoseconds, trillionths of a second. This level of detection technology took decades to develop and continues to improve. The atomic clocks used to time the laser pulses are equally impressive. Modern atomic clocks are accurate to within 1 second over hundreds of millions of years. They tick with such regularity that they can measure time intervals of billionths of a second with confidence. Without these clocks, lunar laser ranging would be impossible. The entire measurement depends on knowing exactly when the laser pulse was sent and exactly when the return photon arrived. All of this technology developed over decades by thousands of scientists and engineers, came together to answer what seems like a simple question. Is the moon moving away from Earth? And the answer, confirmed by over 50 years of measurements, is yes. The moon is receding at 3.8 centimeters per year. This number has been verified again and again by different teams using different methods at different times. It is one of the most precisely measured quantities in astronomy. But lunar laser ranging is not the only way we know the moon is moving away. There are other lines of evidence, some of them much older than the space age. Astronomers have been carefully observing the moon for centuries. Historical records of lunar eclipses, dating back to ancient Babylon, provide a window into the moon's past orbit. The Babylonians were meticulous record keepers. They noted the dates and times of eclipses on clay tablets, many of which have survived to the present day. The oldest reliable eclipse records date back to about 747 BCE, nearly 3,000 years ago. By comparing the timing and locations of these ancient eclipses with what we would expect based on the moon's current orbit, astronomers can detect changes in the Earth-Moon system over thousands of years. The calculations are complex. You have to account for changes in Earth's rotation, uncertainties in the ancient calendars, and the exact locations where the eclipses were observed. But when all of these factors are carefully considered, the ancient eclipse records tell a consistent story. The moon's orbit has been changing over historical time. Chinese astronomers also kept detailed records for over 2,000 years. Greek astronomers like Hipparchus made precise measurements of the moon's position in the 2nd century BCE. Medieval Islamic astronomers continued this tradition with even greater accuracy. All of these historical records provide data points that help us understand how the Earth-Moon system has evolved. When modern astronomers analyze these ancient records, they find that the eclipses do not quite match what we would expect if the moon had always been at its current distance and the Earth had always rotated at its current rate. The discrepancies are small, but detectable. An eclipse that occurred in ancient Babylon should have been visible at a certain location and time based on the moon's current orbital parameters. But the ancient records show it occurred at a slightly different time or was visible from a slightly different location. These small differences, accumulated over thousands of years of eclipse records, provide independent confirmation that the moon is slowly moving away and that Earth's rotation is slowly changing. There is another source of evidence that takes us even further back in time: tidal rhythmites. These are sedimentary rock formations that preserve a record of ancient tides. As tides rise and fall, they deposit layers of sediment. Each tidal cycle leaves a slightly different layer, and these layers build up over time, creating a geological record of tidal patterns. The process works like this. When the tide comes in, it carries fine sediment particles suspended in the water. As the tide reaches its highest point and begins to retreat, the water slows down and the sediment settles out, forming a thin layer. Each tidal cycle deposits one layer. Over time, thousands upon thousands of these layers accumulate, forming a sequence of alternating bands that record the rhythm of the tides. But tides are not simple. There are daily tides, caused by Earth's rotation beneath the tidal bulges. There are spring tides and neap tides, caused by the alignment of sun and moon. There are monthly variations as the moon moves closer and farther in its elliptical orbit. All of these cycles leave their signatures in the sedimentary record, creating complex patterns that can be decoded by careful analysis. By studying tidal rhythmites from different geological periods, scientists can estimate the length of the day and the distance to the moon in the distant past. The results are striking and consistent with what the laser ranging tells us. Rocks from about 620 million years ago, from a period called the Late Precambrian, suggest that days were only about 21.9 hours long. Going further back, rocks from about 900 million years ago indicate days of about 18 hours, and the very oldest tidal rhythmites, from about 2.5 billion years ago, suggest days as short as 17 hours. These ancient rocks are telling us the same story as the modern laser measurements. The moon was closer in the past. Earth rotated faster. Days were shorter. The Earth-Moon system has been evolving throughout Earth's history, and that evolution has been in the same direction. The moon moving away, Earth slowing down. Coral fossils provide yet another line of evidence. Corals deposit daily and annual growth bands in their skeletons, similar to the way trees form annual rings. By counting these bands in fossil corals from different geological periods, scientists can estimate how many days there were in a year at different times in Earth's history. The length of the year has not changed significantly because it depends on Earth's orbit around the Sun, which is very stable. So if there were more days in a year in the past, that means days were shorter. The math is straightforward. If there were 400 days in a year instead of 365, then each day was about 9% shorter, roughly 22 hours instead of 24. Corals from the Devonian period, about 380 million years ago, show that there were about 400 days in a year. This implies days of about 22 hours. Earlier corals from the Ordovician period, about 450 million years ago, show about 412 days per year, implying days of about 21.3 hours. All of this evidence from ancient eclipses, from tidal rhythmites, from coral fossils, points in the same direction as the laser ranging measurements. The moon has been moving away from Earth throughout history. Earth's rotation has been slowing down throughout history. The rate has varied over time, but the direction has been consistent. Our cosmic companion is slowly but surely drifting into the darkness. The implications of this discovery are profound. It means that the Earth-Moon system is not static. It is not fixed. It is not eternal and unchanging. The relationship between our planet and its satellite has been changing for billions of years, and will continue to change for billions more. The moon you see tonight is farther away than the moon your grandparents saw, and your grandchildren will see a moon slightly farther still. The measurement of the moon's recession is also a triumph of human ingenuity and persistence. Think about what it took to make these measurements possible. First, we had to develop rockets powerful enough to send humans to the moon, an achievement that required the efforts of hundreds of thousands of people and the resources of a superpower. Then, we had to design retroreflectors that would survive the lunar environment for decades, exposed to temperature extremes, radiation, and micrometeorite bombardment. We had to build lasers powerful enough to send detectable signals across nearly 400,000 kilometers of space. We had to develop detectors sensitive enough to catch single photons returning from the moon. And we had to build atomic clocks precise enough to time these round trips to billionths of a second. All of this technology, the culmination of centuries of scientific and engineering progress, came together to answer a question that humans have wondered about for millennia. What is the moon doing? Where is it going? Is it staying put? Or is it changing? The answer is that it is changing. The moon is leaving. Not quickly, not dramatically, but steadily and measurably. 3.8 centimeters per year. Every year. For billions of years past and billions of years to come. This might seem like a small number. And in human terms, you will not notice the moon getting any smaller in your lifetime. The change is far too gradual for that. Your eyes cannot detect a difference of 3 meters in a distance of nearly 400,000 kilometers. But over geological time, over billions of years, this slow recession adds up to something enormous. When the moon first formed, it was much closer to Earth, perhaps as close as 20,000 kilometers, though estimates vary depending on the details of the formation model. At that distance, the moon would have appeared about 15 to 20 times larger in angular diameter than it does today. It would have been a massive presence, dominating the heavens, raising enormous tides, and profoundly affecting conditions on the young Earth. Over the following billions of years, the moon has been slowly spiraling outward, driven by the same mechanism that continues to operate today. It has moved from that close initial distance to its current position nearly 400,000 kilometers away. And it continues to move outward, 3.8 centimeters at a time, year after year, eon after eon. This is one of the most fundamental processes shaping the Earth-Moon system. It has been going on since the beginning. It will continue until the end. And we can measure it, with lasers and mirrors, to an accuracy of millimeters. The retroreflectors left on the moon by Apollo astronauts are still working today, more than 50 years after they were deployed. They require no power, no maintenance, no human intervention. They simply sit there on the lunar surface, reflecting laser beams back to Earth whenever someone aims a laser at them. They are silent witnesses to one of the most fundamental processes in the solar system, the slow, inexorable transfer of angular momentum from Earth to Moon, the gradual widening of the lunar orbit, the cosmic dance that has been going on since the Moon first formed from the debris of an ancient collision. Every time a laser pulse bounces off those reflectors and returns to Earth, it carries information about this dance. It tells us exactly where the moon is, how fast it is moving, and how its orbit is changing. It confirms with millimeter precision that our companion is slowly leaving us, and that departure, that slow recession, is one of the most elegant examples of physics in action that exists anywhere in the cosmos. But why? Why is the moon moving away? What is the mechanism that connects the tides to the moon's orbit? How can water sloshing on Earth's surface possibly affect a massive rocky body nearly 400,000 kilometers away? The answer involves the transfer of angular momentum through tidal forces. It connects the rotation of Earth to the orbit of the moon. It ties together gravity, momentum, and energy in a dance that has been going on for 4.5 billion years. And understanding this mechanism reveals one of the most beautiful and counterintuitive phenomena in all of physics. To understand why the moon is moving away from Earth, we need to understand tides. Not just the tides you see at the beach, not just the rising and falling of water along the shore, but tides in a deeper, more fundamental sense. Because tides are not just about water sloshing back and forth. They are about gravity. They are about the shape of worlds. They are about the transfer of energy and momentum across the vast emptiness of space. The tides connect Earth and Moon in a gravitational embrace that has been reshaping both bodies for billions of years. Let us start with a simple question. What causes tides? The standard explanation goes something like this. The moon's gravity pulls on Earth. This gravitational pull is stronger on the side of Earth closest to the moon and weaker on the side farthest from the moon. This difference in gravitational pull creates a stretching effect that raises bulges of water on opposite sides of Earth. As Earth rotates beneath these bulges, different locations experience high tide and low tide twice each day. This explanation is correct as far as it goes, but it only scratches the surface of what tides really are and what they really do. To understand how tides can move something as massive as the moon, we need to go much deeper into the physics. We need to understand not just what tides are, but how they transfer energy and momentum between rotating and orbiting bodies. First, let us think about what a tide really is at its most fundamental level. A tide is a deformation. It is a change in shape caused by differential gravitational forces. When we say differential gravitational forces, we mean that gravity does not pull equally on all parts of an extended object. The strength of gravity depends on distance. The closer you are to a massive object, the stronger its gravitational pull. The farther you are, the weaker the pull. Earth is not a point. It is a sphere nearly 13,000 kilometers in diameter. The side of Earth facing the moon is about 6,371 kilometers closer to the moon than the center of Earth is. The side facing away from the moon is about 6,371 kilometers farther from the moon than the center is. This means the moon's gravitational pull is noticeably stronger on the near side of Earth than on the far side. This difference in gravitational force across the body of Earth is called a tidal force. It is not the absolute strength of gravity that matters for tides. What matters is the difference in gravity from one point to another. This differential force tends to stretch objects along the line connecting them to the gravitating body. It pulls the near side toward the moon more strongly than it pulls the center. It pulls the center more strongly than it pulls the far side. The net effect is a stretching, an elongation along the Earth-Moon line. This is why tides raise bulges on both the near side and the far side of Earth, not just on the near side. Many people find this counterintuitive. They understand why the moon's gravity would pull water toward the moon on the near side. But why would there be a bulge on the far side, pointing away from the moon? The answer is that the far side bulge is not really being pulled away from the moon. It is being left behind. The center of Earth is being pulled toward the moon more strongly than the far side is. So relative to the center of Earth, the far side is falling behind. It is as if the center of Earth is being pulled out from under the far side, leaving a bulge behind. The result is two bulges, one pointing toward the moon and one pointing away from it, with slightly lower water levels in between. Now, if Earth were a perfectly fluid body with no internal friction, these tidal bulges would align exactly with the moon. The bulge on the near side would point directly at the moon. The bulge on the far side would point directly away. The bulges would be perfectly symmetric, and as Earth rotated, the bulges would stay fixed relative to the moon, always pointing along the Earth-Moon line. But Earth is not a perfectly fluid body. The oceans are fluid, yes, but they are bounded by continents. They have varying depths from shallow coastal shelves to abyssal plains several kilometers deep. They are separated into distinct basins by land masses, and most importantly, water has inertia. It cannot instantly rearrange itself to match the moon's position. It takes time for the oceans to respond to the changing gravitational forces as Earth rotates and the moon moves along its orbit. This delay is absolutely crucial to understanding why the moon is moving away. Because of friction and inertia, the tidal bulges do not align exactly with the moon. They lag behind. The bulge that should point directly at the moon actually points slightly ahead of the moon, carried forward by Earth's rotation. And the bulge on the far side points slightly behind where it should be. Let me explain this more carefully because it is the key to everything. Earth rotates on its axis once every 24 hours. This rotation is counterclockwise when viewed from above the North Pole. The moon orbits Earth once every 27.3 days, also counterclockwise when viewed from above the North Pole. This means Earth is rotating much faster than the moon is orbiting. Every day, Earth completes one full rotation while the moon moves only about 13 degrees along its orbit. Now imagine the tidal bulge on the near side of Earth. If there were no friction, this bulge would point directly at the moon at all times. But because of friction between the ocean water and the ocean floor, the bulge cannot keep up with the moon's position. Earth's rotation carries the bulge forward, ahead of where it should be. The water tries to flow back toward its equilibrium position directly beneath the moon, but it cannot flow fast enough. Friction drags it along with Earth's rotation. The result is that the tidal bulge on the near side does not point directly at the moon. It points slightly ahead of the moon, offset in the direction of Earth's rotation. The typical offset is only about 2 to 3 degrees, which does not sound like much, but that small offset has enormous consequences. Here is where the physics becomes beautiful. That tidal bulge has mass. It is a concentration of water, slightly higher than the surrounding ocean. And because it has mass, it exerts gravitational force. Everything with mass attracts everything else with mass. That is Newton's law of universal gravitation. So the tidal bulge, this pile of water raised by the moon's gravity, pulls back on the moon. But here is the crucial point. Because the bulge is offset ahead of the moon, it does not pull the moon directly toward Earth. It pulls the moon slightly forward in the direction of the moon's orbital motion. The near side bulge is ahead of the moon, so its gravitational pull on the moon has a component in the forward direction. This is a small force, but it is persistent. Every moment of every day, that offset tidal bulge is pulling the moon forward, giving it a tiny gravitational boost in the direction it is already moving. When you boost something in its orbital direction, you add energy to its orbit. This is how spacecraft raise their orbits. They fire their engines in the direction they are moving, adding velocity, and this causes them to move to a higher orbit. The same principle applies to the moon. The gravitational pull from the offset tidal bulge adds energy to the moon's orbit. And when you add energy to an orbit, the orbit expands. The object moves to a higher, more distant orbit. This is why the moon is moving away from Earth. The misaligned tidal bulge on Earth is continuously giving the moon a tiny gravitational acceleration forward. This acceleration adds energy to the moon's orbit, causing it to spiral slowly outward, 3.8 centimeters per year, year after year, for billions of years. But wait, there is another side to this interaction. Newton's third law states that every action has an equal and opposite reaction. If the tidal bulge is pulling the moon forward, then the moon must be pulling backward on the tidal bulge. The forces are equal and opposite. The moon is exerting a gravitational pull on the tidal bulge that is opposite to the bulge's pull on the moon. This backward pull from the moon on the offset tidal bulge creates a torque on Earth. A torque is a twisting force that causes rotation to speed up or slow down. The moon's gravitational pull on the tidal bulge acts against Earth's rotation. It is trying to slow Earth down, trying to pull the bulge back toward alignment with the moon. And because this torque acts continuously, it gradually reduces Earth's rotation rate. This is the other half of the mechanism. The same tidal interaction that is pushing the moon outward is also slowing Earth's rotation. The moon is gaining orbital energy and angular momentum. Earth is losing rotational energy and angular momentum. The two effects are connected. They are two sides of the same coin. Angular momentum is a quantity that measures rotational motion. For a spinning object like Earth, angular momentum depends on how fast the object is rotating and how its mass is distributed. For an orbiting object like the moon, angular momentum depends on how fast it is orbiting and how far it is from the center of its orbit. Angular momentum is conserved in closed systems. This means the total angular momentum cannot be created or destroyed. It can only be transferred from one part of the system to another. In the Earth-Moon system, the total angular momentum is approximately conserved. As Earth's rotation slows down, Earth loses angular momentum. That angular momentum does not disappear. It is transferred to the moon, which gains orbital angular momentum. When the moon gains orbital angular momentum, it moves to a higher orbit. This is the fundamental conservation law underlying the moon's recession. Let me give you some numbers to make this concrete. Earth's rotation is slowing down at a rate of about 1.4 milliseconds per century. That might not sound like much. After all, what is 1.4 milliseconds? That is 1,400 microseconds. That is 14 ten-thousandths of a second. You cannot even perceive a time interval that short. A blink of an eye takes about 300 milliseconds. 1.4 milliseconds is about 200 times shorter than a blink. But over long periods, even this tiny rate of change adds up. 100 million years ago, a day on Earth was about 23 hours long instead of 24. That is because days were shorter by about 1.4 milliseconds for each century of those 100 million years. 500 million years ago, days were only about 21 hours long. Go back far enough to when the moon first formed, and days were perhaps only 5 or 6 hours long. All of this rotational energy that Earth has lost over billions of years has gone into the moon's orbit. It has been converted into orbital energy, pushing the moon farther and farther from Earth. The tidal bulges are the mechanism that mediates this transfer. They are the connection between Earth's spin and the moon's orbit. They are the channel through which angular momentum flows from one body to the other. The tidal bulge on Earth is not the only source of tidal dissipation. The moon also raises tides in Earth's solid body, not just in the oceans. These solid Earth tides are smaller than ocean tides, typically only about 20 centimeters of vertical displacement compared to meters for ocean tides. But they contribute to the total tidal dissipation. The solid Earth flexes slightly as the moon passes overhead, and this flexing generates heat through internal friction in the rocks. There are also tides on the moon itself. Earth's gravity raises tidal bulges on the moon, just as the moon's gravity raises tidal bulges on Earth. But the moon's tides work differently now because the moon is tidally locked to Earth. Tidal locking means the moon rotates at exactly the same rate it orbits. The moon takes 27.3 days to complete one orbit around Earth. It also takes 27.3 days to complete one rotation on its axis. This means the moon always shows the same face to Earth. The near side of the moon is always the near side. The far side is always the far side. The moon does not spin independently like Earth does. Its rotation and orbit are synchronized. This synchronization happened because of tidal forces. Long ago, shortly after the moon formed, it was rotating faster than it orbited. Just like Earth today, the tidal bulges raised on the moon by Earth's gravity were offset, just like the tidal bulges on Earth raised by the moon's gravity. These offset bulges created torques that slowed the moon's rotation. Over millions of years, the moon's rotation slowed until it matched its orbital period. Once this happened, the tidal bulges on the moon became fixed relative to Earth. They no longer needed to slosh back and forth as the moon rotated beneath them. The dissipation stopped. The moon became locked. Today, because the moon is tidally locked, the tidal bulges on the moon are essentially stationary relative to Earth. They point directly at Earth and directly away from Earth. There is no offset, and therefore no torque. Almost all the tidal dissipation in the Earth-Moon system now happens on Earth, primarily in the oceans. How much energy is being dissipated by the tides? The total rate of tidal dissipation on Earth is about 3.1 terawatts. That is 3.1 trillion watts. To put this in perspective, the total electrical power consumption of human civilization is about 18 terawatts. The tides dissipate about 1/6 as much power as all of humanity uses. Where does this energy go? Most of it ends up as heat. The friction between tidal currents and the ocean floor generates heat. Turbulence in tidal flows generates heat. Internal friction as the solid Earth flexes generates heat. All of this heat is ultimately radiated away into space. It is lost, gone. The energy that once resided in Earth's rotation is converted to heat and dissipated into the cosmos. This energy dissipation is what drives the whole process. Energy flows from Earth's rotation through the tidal bulges and ultimately into heat. Some fraction of the energy goes into the moon's orbit, increasing its orbital energy, but most is lost to friction. This loss is what allows angular momentum to transfer from Earth to Moon. Without dissipation, without friction, angular momentum could not flow. The system would oscillate but not evolve. Most of the tidal dissipation comes from the oceans, particularly from shallow seas and continental shelves where tidal currents are strongest. The water in shallow regions moves faster because the same volume of water must flow through a smaller cross-sectional area. Faster currents mean more friction against the ocean floor. More friction means more energy dissipation. The North Atlantic is one of the most important regions for tidal dissipation. The tidal wave that crosses the Atlantic reflects off the European and African coasts and interferes with itself, creating complex patterns of high and low tides. The shallow waters around the British Isles, the English Channel, and the North Sea are particularly efficient at dissipating tidal energy. The Bay of Fundy in Canada, famous for having some of the highest tides in the world, is another significant site of tidal dissipation. The seas around Indonesia and Australia are also major contributors. The complex coastlines and numerous islands create narrow straits through which enormous volumes of water must flow with each tide. The friction in these straits dissipates significant amounts of energy. Interestingly, the rate of tidal dissipation, and therefore the rate of the moon's recession, is not constant over geological time. It depends on the configuration of the continents, the depth of the oceans, and the geometry of coastlines. Today, The continents are arranged in a way that creates relatively high tidal dissipation. The Atlantic Ocean is narrow enough that tidal waves can resonate, amplifying tidal amplitudes. Shallow seas and complex coastlines provide plenty of opportunities for frictional dissipation, but the continents have not always been in their current positions. Throughout Earth's history, they have drifted across the planet's surface, coming together to form supercontinents and then breaking apart again. Each configuration creates different patterns of tidal flow and different rates of tidal dissipation. When there was a single supercontinent like Pangaea, about 250 million years ago, tidal dissipation may have been lower. With no narrow ocean basins to create resonances and fewer shallow seas, the tides would have behaved differently. The moon's recession rate would have been different too, perhaps slower, perhaps faster. It depends on the specific geometry. Going even further back, when there were no continents at all, when Earth's surface was covered by a global magma ocean, tidal dissipation would have been dominated by the viscosity of molten rock rather than the friction of water. The rates would have been very different from today, perhaps much higher, given the intense tidal forces when the moon was close. This means that the moon's recession has not been steady throughout Earth's history. The rate has varied as Earth's geography has changed. Sometimes the moon moved away faster, sometimes slower. The current rate of 3.8 centimeters per year is specific to the current configuration of continents and oceans. In fact, when scientists try to calculate the moon's past position using the current recession rate and extrapolating backward, they encounter a problem. If the moon had always receded at 3.8 centimeters per year, it would have been touching Earth only about 1.5 billion years ago. But we know the moon is about 4.5 billion years old. The moon cannot have been touching Earth 1.5 billion years ago, because it had already been orbiting for 3 billion years by then. This discrepancy tells us that the recession rate must have been slower in the past on average. The current rate of tidal dissipation is higher than the historical average. Today's continental configuration creates particularly efficient tidal dissipation. In the past, when continents were arranged differently, dissipation was often lower and the moon receded more slowly. Studies of tidal rhythmites and other geological evidence support this conclusion. The recession rate has varied throughout Earth's history, sometimes faster and sometimes slower, depending on the arrangement of the continents and the properties of the oceans. This variability adds complexity to our understanding of the Earth-Moon system's history, but it does not change the fundamental physics. The mechanism is the same regardless of the rate. Tidal bulges offset by friction create torques. These torques transfer angular momentum from Earth's rotation to the moon's orbit. The rate at which this transfer occurs varies depending on how efficiently tidal energy is dissipated, but the direction is always the same. The moon is always moving away. Earth's rotation is always slowing down. Let me describe the energy flow more precisely because it reveals something subtle and important. Earth's rotation carries the tidal bulge ahead of the moon. The moon's gravity pulls back on this bulge, creating a torque that slows Earth's rotation. At the same time, the bulge's gravity pulls forward on the moon, adding energy to its orbit. The energy comes from Earth's rotational kinetic energy. Some of it goes into the moon's orbital energy. The rest is dissipated as heat through tidal friction. Here is something that might seem paradoxical. When the moon moves to a higher orbit, it actually moves slower. Objects in higher orbits move more slowly than objects in lower orbits. This is a fundamental property of orbital mechanics. How can adding energy to the moon's orbit cause it to slow down? The answer lies in the nature of gravitational orbits. An object in orbit has two kinds of energy. It has kinetic energy from its motion, and it has potential energy from its position in the gravitational field. For a gravitationally bound orbit, the total energy is negative. This means the object is bound. It cannot escape. As you move to a higher orbit, you gain potential energy because you are farther from the gravitating body, but you lose kinetic energy because you are moving slower. The total energy increases, becoming less negative, but the kinetic energy, the energy of motion, actually decreases. This is why the moon moves slower in a higher orbit. As angular momentum is transferred from Earth to moon, the moon's orbit expands. The moon gains potential energy but loses kinetic energy. Its orbital velocity decreases. The moon currently orbits Earth at about 1.02 kilometers per second. Billions of years ago, when it was much closer, it orbited much faster. And billions of years in the future, when it is farther away, it will orbit even more slowly. Meanwhile, the energy dissipated through tidal friction heats Earth's interior and oceans by a tiny amount. This is a small amount of heat compared to other sources like solar radiation and radioactive decay in Earth's interior, but it is real. The tides are warming the oceans, imperceptibly but measurably, and every bit of that warmth is energy that was once part of Earth's rotation. The Earth-Moon system is like a slowly unwinding clock. Earth's rotation is the spring that powers the clock. Tidal dissipation is the mechanism that releases energy from the spring. And the moon's outward motion is the result, like the hands of the clock slowly turning as the spring unwinds. This clock has been running for 4.5 billion years. It still has billions of years left to run, but it will eventually wind down. The spring will eventually lose all its tension. Earth's rotation will eventually slow to match the moon's orbital period, and the tidal dissipation will stop. When that happens, both Earth and moon will be tidally locked to each other. Earth will always show the same face to the moon. The moon already always shows the same face to Earth. The tidal bulges will align perfectly, with no offset to create torques. The system will reach equilibrium. Angular momentum will no longer transfer. The moon will stop moving away. But that is billions of years in the future. For now, the clock continues to tick. The spring continues to unwind. And the moon continues its slow journey outward, pushed by the same mechanism that has been operating since the moon first formed. The physics of tidal interactions is elegant and universal. It is not unique to Earth and Moon. It operates wherever gravitationally bound bodies exist, close enough to raise tides on each other. Every moon in the solar system that is close enough to its planet experiences tidal effects. Many of these moons are tidally locked to their planets, just as our moon is locked to Earth. Jupiter's moon Io provides a dramatic example of tidal physics in action. Io orbits very close to Jupiter, one of the most massive planets in the solar system. The tidal forces from Jupiter are enormous, but Io is also gravitationally perturbed by the other large moons of Jupiter, Europa, and Ganymede. These perturbations prevent Io's orbit from becoming perfectly circular. The varying distance to Jupiter means that tidal forces on Io constantly change, flexing the moon's interior. This tidal flexing generates enormous amounts of heat through friction in Io's rocks. So much heat that Io is the most volcanically active body in the solar system. Its surface is covered with hundreds of active volcanoes, constantly erupting and resurfacing the moon. The energy for all this volcanism comes from tidal dissipation. Jupiter's gravity is literally squeezing Io and heating it up. Europa, another of Jupiter's moons, also experiences tidal heating, though less intense than Io's. This heating is thought to maintain a liquid water ocean beneath Europa's icy surface. The ice shell insulates the ocean from the cold of space, and tidal heating keeps the interior warm enough for liquid water to exist. This makes Europa one of the most promising places in the solar system to search for extraterrestrial life. Saturn's moon, Enceladus, is another world where tidal heating has profound effects. Geysers of water ice erupt from fractures near Enceladus's south pole, spraying material hundreds of kilometers into space. These geysers are direct evidence of a liquid water ocean beneath the icy surface, maintained by tidal heating. The Cassini spacecraft flew through these geysers and detected complex organic molecules, further increasing interest in Enceladus as a potential habitat for life. In binary star systems, tidal interactions can transfer mass and angular momentum between the stars. Closed binary stars can become tidally locked to each other, always showing the same faces. In extreme cases, tidal forces can strip material from one star and deposit it onto the other, changing the masses and orbits of both stars over time. In exoplanet systems, tidal interactions determine whether planets become tidally locked to their stars. Many planets orbiting close to red dwarf stars are thought to be tidally locked, always showing the same face to their star. One hemisphere experiences permanent day, the other experiences permanent night. The implications for climate and potential habitability are profound, and are the subject of intense research. The physics of tidal interactions is universal. It operates wherever gravity connects rotating or orbiting bodies, and it always works the same way. Differential gravitational forces create bulges. If those bulges are offset from the line connecting the bodies, torques arise. These torques transfer angular momentum and energy between rotation and orbit. Friction dissipates energy and allows the transfer to proceed. For the Earth-Moon system, the result is a slow outward spiral of the Moon and a gradual slowing of Earth's rotation. 3.8 centimeters per year, 1.4 milliseconds per century. Numbers that seem tiny on human timescales, but are enormous when accumulated over billions of years. The mechanism connecting tides to the Moon's motion is one of the most elegant examples of physics in action. It ties together gravity, rotation, orbital mechanics, fluid dynamics, and thermodynamics into a single, coherent process. It connects something as familiar as ocean tides to something as cosmic as the evolution of the Earth-Moon system over billions of years. Every tide you've ever seen is part of this process. Every time the water rises on a beach, energy is being extracted from Earth's rotation. Every time tidal currents flow through narrow straits, friction is dissipating energy. Every moment, angular momentum is flowing from Earth to Moon, and the Moon is drifting a tiny bit farther away. The tides are not just a curiosity. They are not just a phenomenon for surfers and fishermen to track. They are a cosmic engine, slowly but surely reshaping the relationship between Earth and its companion. They have been operating for 4.5 billion years. They will continue to operate for billions more. And in their patient, persistent action, they are writing the history and the future of the Earth-Moon system. The Moon has not always been where it is now. It has not always been a distant companion hanging serenely in our night sky. In the distant past, billions of years ago, the Moon was close, terrifyingly close by today's standards. It loomed enormous in the sky, raising tides that would dwarf anything we experience today, shaping the young Earth in ways that were almost impossible to imagine. To understand where the Earth-Moon system came from, we need to travel back in time, back before the first life appeared, back before the oceans formed, back to a time when Earth itself was barely recognizable, back to the moment of the Moon's violent birth. The story begins about 4.5 billion years ago, when the solar system was a very different place than it is today. The Sun had recently ignited, beginning its long career as a stable, hydrogen-burning star. But the planets were still forming from the disk of gas and dust that surrounded the young Sun. This proto-planetary disk was a chaotic environment, filled with debris ranging from microscopic dust grains to objects hundreds of kilometers across. These objects were constantly colliding, sometimes destroying each other in catastrophic impacts, sometimes merging to form larger bodies. The inner solar system was especially violent, where Mercury, Venus, Earth, and Mars now follow orderly orbits. There was chaos. Dozens of planetary embryos, objects roughly the size of the Moon or Mars, swept through the inner solar system on crossing orbits. Collisions were frequent. Some embryos were destroyed. Others grew larger by absorbing the debris from collisions. Over millions of years, this process of collision and accumulation gradually built the terrestrial planets we know today. Earth had mostly finished forming by about 4.5 billion years ago. It was a rocky planet, somewhat smaller than it is today, with a molten surface covered by a global magma ocean. There was no atmosphere as we would recognize it, just a thin envelope of vaporized rock and volcanic gases. There were no oceans of water. The surface was too hot. Water that existed was either locked in rocks or lost to space. And there was no moon. Earth spun alone through the young solar system. But Earth was not the only large body in its region of the solar system. According to the leading theory of lunar formation, there was another planet-sized object in roughly the same orbital zone. Astronomers have named this hypothetical world Theia, after the Greek Titan goddess who was the mother of Selene, the goddess of the moon. The name is fitting. Theia would become the mother of our moon, though in the most violent way imaginable. Theia was roughly the size of Mars, about half the diameter of Earth. It had its own iron core, its own rocky mantle, its own history of formation through collision and accretion. For millions of years, Earth and Theia followed similar orbits around the Sun, their paths gradually bringing them closer and closer together. The gravitational interactions between them were complex. Sometimes they passed close to each other without colliding. Sometimes their orbit shifted slightly due to these close encounters, but eventually, inevitably, their paths intersected. About 4.5 billion years ago, Theia struck Earth. This was not a glancing blow. This was not a minor collision. This was one of the most catastrophic events in the history of the solar system. Theia struck Earth at an angle of roughly 45 degrees, moving at a velocity of about 4 kilometers per second. That is about 14,400 kilometers per hour. Faster than any bullet. Faster than any spacecraft humans have ever built. The energy released by this impact is almost impossible to comprehend. When Theia struck Earth, the kinetic energy of its motion was converted into heat in an instant. The impact released energy equivalent to billions upon billions of nuclear weapons, detonating simultaneously. Both worlds were essentially liquefied by the collision. The solid rock of both planets was vaporized at the point of impact and melted throughout their interiors. The impact excavated enormous amounts of material from both Earth and Theia. Much of this debris was vaporized rock, thrown into space at tremendous velocities. Some of it escaped the Earth-Theia system entirely, flying off into the solar system never to return. Some of it fell back to the shattered, molten Earth, adding to the planet's mass. But a significant fraction went into orbit around what remained of Earth. This orbiting debris formed a ring around Earth. But this was not a ring like Saturn's rings, made of ice and rock fragments. This was a ring of fire, a ring of vaporized and molten rock extending from just above Earth's surface out to tens of thousands of kilometers. The temperatures in this ring were thousands of degrees. The debris glowed white hot, illuminating the devastated Earth below with a hellish light. And then, something remarkable happened. This ring of debris began to coalesce. Gravity pulled the material together. Within this ring, denser regions attracted more material, growing larger and larger. Computer simulations suggest that the moon may have formed in an astonishingly short time, perhaps as little as a few hours to a few days after the impact. The debris was so hot and so dense that gravitational attraction quickly pulled it together into a single body. The moon that emerged from this cosmic catastrophe was very different from the moon we know today. It was much closer to Earth, perhaps only about 20,000 to 30,000 kilometers away. That is less than 1/10 of its current distance. At that distance, the moon would have appeared enormous in Earth's sky. Depending on the exact initial distance, it might have appeared 15 to 20 times larger in angular diameter than it does today. Imagine looking up and seeing a moon that fills a huge portion of the sky. Not the modest disk we see today, but a massive presence that dominates the heavens. During the day, this giant moon would have been visible even against the bright sky. At night, when full, it would have flooded the landscape with light many times brighter than the full moon does today. The phases of this giant moon would have been dramatic events, transforming the appearance of the sky from day to day. But the young moon did not stay at that distance. Almost immediately after forming, tidal interactions began to push it outward. The physics was the same as what operates today, but the rates were enormously higher. The young Earth was rotating extremely fast, perhaps completing one rotation every 5 or 6 hours. The moon was orbiting even faster than that because it was so close, and the tidal bulges raised on both bodies were enormous, generating tremendous torques that transferred angular momentum rapidly. In the early Earth-Moon system, both bodies were largely molten. Earth was covered by a global magma ocean, thousands of kilometers deep. The moon was similarly molten, its interior heated by the energy of its violent formation. In molten rock, tidal bulges can be enormous. The viscosity of magma is much lower than the viscosity of solid rock, allowing the material to flow and deform much more readily. The tidal bulges in Earth's magma ocean were probably hundreds of meters high, vastly larger than the few meters of today's ocean tides. These enormous tidal bulges generated correspondingly enormous torques. Angular momentum flowed rapidly from Earth's rotation to the moon's orbit. Within the first few million years after the impact, the moon probably moved out to a distance of about 60,000 kilometers. Within the first 100 million years, it may have been at about 100,000 kilometers. The recession was rapid at first, then gradually slowed as the moon moved farther away and the tidal forces weakened. The slowing of the recession rate is a natural consequence of the physics. Tidal forces decrease with the cube of the distance. If you double the distance, the tidal force decreases by a factor of 8. If you increase the distance by 10 times, the tidal force decreases by a factor of 1,000. As the moon moved outward, the tidal forces it exerted on Earth became weaker and weaker. Weaker tidal forces meant smaller tidal bulges. Smaller bulges meant less torque. Less torque meant slower transfer of angular momentum. The recession rate dropped. During this early period, conditions on Earth were extreme beyond anything we can easily imagine. The planet was largely molten, covered in a magma ocean that glowed red and orange with heat. The sky was filled with a giant moon that raised tides not in water, but in liquid rock. These tidal bulges in the magma ocean would have been enormous, perhaps hundreds of meters high, constantly kneading the young Earth's interior. The gravitational interaction between Earth and Moon during this early period was intense. The Moon's gravity distorted Earth's shape, elongating it along the Earth-Moon line. Earth's gravity did the same to the Moon. Both bodies were constantly flexing, their shapes changing as they rotated and orbited. This flexing generated heat through internal friction, adding to the already extreme temperatures of the young Earth-Moon system. As millions of years passed, both Earth and Moon began to cool. The magma oceans gradually solidified as heat radiated away into space. A solid crust began to form on Earth's surface, though it was probably repeatedly destroyed and reformed by continuing impacts from leftover debris in the solar system. The Moon cooled more quickly because it is smaller and has less internal heat to lose. Within a few 100 million years, the Moon had developed a solid crust, though its interior remained partially molten for much longer. The Moon also became tidally locked to Earth during this early period. Initially, the Moon was rotating faster than it was orbiting, just as Earth was rotating faster than the Moon was orbiting. The tidal bulges raised on the Moon by Earth's gravity were offset, and the resulting torques slowed the Moon's rotation. Because the Moon is much smaller than Earth, and because the tidal forces from Earth on the Moon were stronger than the tidal forces from the Moon on Earth, the Moon reached tidal lock much faster than Earth is approaching it. Within probably the first 100 million years, the Moon's rotation had slowed to match its orbital period. From that point on, the Moon always showed the same face to Earth. The tidal bulges on the Moon became fixed, no longer needing to slosh around as the Moon rotated beneath them. Tidal dissipation on the Moon essentially stopped. The Moon became locked in its eternal gaze toward Earth. As the Moon continued to move outward, conditions on Earth gradually changed. The magma ocean cooled and solidified. A primitive atmosphere formed from volcanic gases, and eventually, water began to accumulate on the surface. The source of this water is still debated. Some may have been released from Earth's interior as the planet cooled. Some may have been delivered by comets and water-rich asteroids from the outer solar system. Whatever the source, by about 4 billion years ago, Earth had oceans. The formation of liquid water oceans changed the nature of tidal dissipation. Water is much more efficient at dissipating tidal energy than rock is. The friction of water against the ocean floor, the turbulence of tidal currents, the sloshing of water against coastlines, all of these mechanisms extract energy from the tides and convert it to heat. With the formation of oceans, tidal dissipation on Earth probably increased significantly. But even with liquid water oceans, the tides in the early Earth were far more extreme than anything we experience today. The Moon was still much closer than it is now, At 100,000 kilometers, the moon would have been almost 4 times closer than today, and the tidal forces would have been about 60 times stronger. Tides that might be a few meters today would have been tens of meters or more in the early ocean. Let me paint a picture of what Earth might have been like at different points in its history as the moon gradually receded. 4 billion years ago, the moon was perhaps 100,000 kilometers away, only about 1/4 of its current distance. In the sky, it would have appeared about 4 times larger in diameter than today, covering 16 times as much area. When full, it would have been blindingly bright, casting sharp shadows and illuminating the night, almost like day. The phases would have been dramatic visual events, the moon's disk visibly changing shape from night to night. Days were probably about 10 to 12 hours long at this time. Earth was spinning much faster than today. The sun rose, crossed the sky, and set in half the time it takes now. The rhythm of day and night was rapid, pulsing with a quick heartbeat compared to today's slower pace. The tides would have been roughly 60 times stronger than today. If ocean tides today can be a few meters in height, tides 4 billion years ago might have been over 100 meters. Imagine a wall of water 100 meters high, sweeping across the coastal regions twice every short day. These were not gentle risings and fallings of the sea. These were massive movements of water, surging across whatever land existed, reshaping coastlines, and generating enormous currents. The geological effects would have been profound. The constant pounding of extreme tides would have eroded rock at tremendous rates. The mixing of water would have been intense, stirring nutrients and chemicals throughout the ocean. The tidal heating of Earth's interior would have been significant, adding to the heat from radioactive decay and residual heat from formation. Some scientists have proposed that these extreme early tides might have been important for the origin of life. Tidal pools, regions that are alternately flooded and exposed by the tides, experience cycles of wetting and drying. These cycles can concentrate chemicals, drive chemical reactions, and create gradients that might have helped simple molecules assemble into more complex ones. The extreme tides of the early Earth would have created vast tidal zones, regions spanning perhaps hundreds of kilometers between high and low tide marks. These zones might have been natural laboratories for prebiotic chemistry. 2 billion years ago, the moon had moved to perhaps 250,000 kilometers, about 2/3 of its current distance. It would have appeared about 50% larger in the sky than today. Still impressive, but no longer the dominating presence it had been. Days were probably about 18 to 20 hours long. Tides would have been about 3 to 4 times stronger than today. Still dramatically different from modern conditions, but beginning to approach something recognizable. By this time, life had been present on Earth for at least 1 billion years. Simple, single-celled organisms, bacteria and archaea, had colonized the oceans and perhaps some land environments. The first photosynthetic organisms had appeared and were beginning to change Earth's atmosphere by producing oxygen. The rhythm of the tides was woven into the fabric of early life. 1 billion years ago, the moon was close to its current distance. Days were about 20 to 22 hours long. Tides were only moderately stronger than today, perhaps 50% more powerful. The Earth-Moon system was beginning to look familiar. By 500 million years ago, during the Cambrian period when complex multicellular life exploded across the planet, conditions were very similar to today. Days were about 21 hours long. The moon appeared only slightly larger than it does now. The tides were comparable to modern tides. The Earth-Moon system had largely settled into the configuration we know. The geological record preserves evidence of these changes. Tidal rhythmites, sedimentary deposits that record ancient tidal cycles, provide one of the most direct windows into the past of the Earth-Moon system. These deposits form when tides carry sediment back and forth, depositing thin layers with each tidal cycle. Over time, thousands of layers accumulate, creating a detailed record of tidal patterns. By studying the spacing and thickness of layers in tidal rhythmites, scientists can extract information about ancient tidal cycles. The daily cycle of 2 high tides and 2 low tides leaves one pattern. The monthly cycle of spring and neap tides leaves another. The annual cycle of changing tidal patterns leaves yet another. By teasing apart these interlocking cycles, researchers can estimate how many days there were in a month and how many days there were in a year at different times in Earth's history. These ancient rocks, along with coral fossils we discussed earlier, tell the same story as modern laser measurements. The moon was closer. Earth spun faster. The system has been evolving continuously for billions of years. The convergence of evidence from laser ranging, ancient eclipse records, tidal rhythmites, and coral fossils is compelling. All of these independent lines of evidence point in the same direction. The moon has been receding from Earth throughout history. Earth's rotation has been slowing. The relationship between our planet and its satellite has been continuously evolving for 4.5 billion years. The moon's influence on Earth extends far beyond tides. One of the most important effects has been the stabilization of Earth's axial tilt. Earth's rotation axis is tilted about 23.4 degrees relative to the plane of its orbit around the Sun. This tilt is what gives us seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer while the southern hemisphere experiences winter. 6 months later, the situation is reversed. Without the moon, this tilt would not be stable. It would wobble chaotically over millions of years, swinging from nearly 0 degrees to perhaps 90 degrees or more. The gravitational influences of the Sun and other planets would tug on Earth's equatorial bulge, causing the rotation axis to precess and nutate in complex ways. Without a stabilizing influence, these perturbations would accumulate, leading to wild swings in axial tilt over timescales of tens of millions of years. Mars provides a cautionary example. Mars has 2 tiny moons, Phobos and Deimos, but they are far too small to provide any stabilizing influence. As a result, Mars's axial tilt has varied chaotically throughout its history. Computer simulations suggest that Mars's tilt has swung from nearly 0 degrees to over 60 degrees multiple times. These variations would have caused extreme climate changes, with polar regions sometimes experiencing tropical conditions and equatorial regions sometimes experiencing polar conditions. The moon acts as a gravitational stabilizer for Earth. Its gravity interacts with Earth's equatorial bulge, creating a restoring torque that resists changes in axial tilt. This stabilization is not perfect. Earth's axial tilt does vary slightly, oscillating between about 22 degrees and 24.5 degrees over a period of about 41,000 years. But this variation is small compared to what would occur without the moon. This stability has been important for the evolution of life on Earth. Stable seasons mean predictable conditions. Organisms can evolve adaptations for specific climate zones with confidence that those zones will persist. Complex ecosystems can develop with species adapted to seasonal patterns that remain consistent over millions of years. Without the moon, Earth's climate might have been too chaotic for complex ecosystems to develop. For life to diversify and elaborate into the rich biosphere we know. The giant impact that formed the moon was also crucial for Earth's composition and structure. When Theia struck Earth, the collision mixed material from both worlds. Earth's iron core and Theia's iron core merged, sinking to the center of the combined body to form Earth's present core. Lighter materials from both mantles were ejected into space, forming the debris ring that became the moon. The moon is significantly less dense than Earth because it formed mostly from mantle material, which is less dense than core material. Earth has an average density of about 5.5 grams per cubic centimeter, reflecting its large iron core. The moon has an average density of only about 3.3 grams per cubic centimeter. The moon has only a tiny iron core, perhaps just 1 to 2% of its total mass, while Earth's core makes up about 1/3 of its total mass. This difference in composition is direct evidence that the moon formed from a giant impact that preferentially ejected lighter materials while the denser core materials fell into Earth. The impact may also have affected Earth's volatile inventory. Volatiles are elements and compounds that vaporize easily, including water, carbon dioxide, nitrogen, and various other substances important for life. Some scientists argue that the giant impact would have stripped away much of Earth's early atmosphere and boiled off any water present on the surface. The atmosphere and oceans we have today may have accumulated later, delivered by comets and asteroids that continue to bombard Earth for hundreds of millions of years after the moon-forming impact. Others argue that significant volatiles could have survived the impact. The debris disk that formed the moon might have captured some volatiles. Some water might have been locked in minerals that survived the extreme temperatures. The exact consequences of the giant impact for Earth's volatile inventory remain an active area of research. What is clear is that the moon-forming impact was a defining moment in Earth's history. It set the initial conditions for everything that followed. It determined Earth's rotation rate, which has been slowing ever since. It determined the moon's initial distance, from which it has been receding ever since. It affected Earth's composition, its volatile content, and the size of its core. And it created the moon itself, the stabilizer that has helped keep Earth's climate moderate enough for life to flourish. Without the giant impact, without Theia striking Earth 4.5 billion years ago, our world would be profoundly different. There might be no large moon in the sky. Earth's axial tilt might wobble chaotically. The day length might be different. The tides might be non-existent or dominated by the much weaker solar tides. Complex life might never have evolved, or might have evolved along completely different paths. The moon is not just an ornament in our sky, it is a fundamental part of what makes Earth the world it is. The history of the Earth-Moon system is a story of continuous change, from the violent birth of the moon in a catastrophic impact, through the early epoch of extreme tides and rapid rotation, to the more sedate conditions of recent geological time. The relationship between Earth and Moon has been constantly evolving. The Moon has been moving away since the moment it formed. Earth has been slowing down since the moment of the impact. The tides have been weakening for billions of years, and yet, despite all this change, the Earth-Moon system remains stable. The Moon continues to orbit Earth. The tides continue to rise and fall. The moon continues to stabilize Earth's axial tilt. The relationship persists, even as it slowly transforms. Looking back at the ancient past helps us understand the present and anticipate the future. The processes that have been operating for 4.5 billion years continue to operate today. The moon recedes 3.8 centimeters per year, just as it has been receding throughout history. Earth's rotation slows by 1.4 milliseconds per century, just as it has been slowing since the beginning. The physics is the same. Only the rates have changed as the geometry has evolved. The moon you see tonight is the product of 4.5 billion years of history. It formed in fire, in the aftermath of a collision that nearly destroyed the Earth. It has been drifting slowly outward ever since, pushed by the same tidal forces that wash against every shore. It has watched over Earth through all the ages of geological time, through the formation of the first continents and oceans, through the origin and evolution of life, through the rise of consciousness and civilization. And it continues its journey still, drifting slowly away from Earth, year by year, eon by eon. The ancient past flows into the present, and the present flows into the future. The dance of Earth and Moon goes on. We have explored how we know the moon is moving away. We have understood the physics of why it is happening. We have looked back at the distant past to see how the Earth-Moon system has changed over billions of years. Now it is time to look forward. What happens to Earth and Moon in the distant future as this cosmic dance continues to unfold? Where is the moon going? What will happen to Earth's rotation? And how will this slow separation ultimately end? The moon is currently receding at about 3.8 centimeters per year. That is a tiny distance by human standards. You could not perceive such a small change even if you watched the moon every night for your entire life. But the universe operates on timescales far longer than human lives. What seems imperceptible to us becomes transformative over millions and billions of years. If the current recession rate continued unchanged, the moon would move about 38 kilometers farther away every million years. After a billion years, it would be about 38,000 kilometers farther than it is now. After 10 billion years, it would be about 380,000 kilometers farther, roughly doubling its current distance from Earth. These are enormous changes that would profoundly alter the appearance of the moon in our sky and the strength of the tides on Earth. But the rate will not stay constant. As the moon moves farther away, the tidal forces it exerts on Earth become weaker. Tidal forces decrease with the cube of the distance. When you double the distance, the tidal force drops to 1/8 of its original value. Weaker tidal forces mean smaller tidal bulges on Earth. Smaller bulges mean less gravitational torque between Earth and Moon. Less torque means slower transfer of angular momentum. The recession gradually slows down. At the same time, Earth's rotation is slowing. As Earth spins more slowly, the tidal bulges have less offset from the moon's position. Remember, the offset exists because Earth's rotation carries the bulges ahead of where they would naturally point. If Earth rotated more slowly, the bulges would have less time to be carried forward before the tidal forces pulled them back toward alignment. Less offset means less torque. This is another factor that slows the recession. The Earth-Moon system is approaching an end state, a configuration where the tidal interactions that drive the current changes will eventually cease. This end state is called double tidal locking, and it represents the ultimate fate of the Earth-Moon relationship. at least in the absence of external interference. Let me explain what double tidal locking means. The moon is already tidally locked to Earth. Its rotation period equals its orbital period, both about 27.3 days. This is why the moon always shows the same face to Earth. The near side is always the near side. The far side is always the far side. We never see the back of the moon from Earth's surface because the moon rotates exactly once for every orbit it completes. This tidal locking happened long ago, probably within the first 100 million years after the moon formed. The tidal torques from Earth's gravity slowed the moon's rotation until it matched its orbital period. Once locked, the tidal bulges on the moon became stationary relative to Earth. They point directly at Earth and directly away from Earth, with no offset. There is no torque and no further change in the moon's rotation. Earth is heading toward the same fate, just much more slowly. As Earth's rotation slows, it will eventually match the moon's orbital period. When that happens, Earth will be tidally locked to the moon. Earth will always show the same face to the moon, just as the moon always shows the same face to Earth. When both bodies are tidally locked to each other, the tidal bulges will align perfectly. The bulge on Earth will point directly at the moon, with no offset caused by rotation. The bulge on the moon already points directly at Earth. There will be no torques. No angular momentum will transfer. The orbital distance will stop changing. The system will have reached equilibrium. This is the distant future of the Earth-Moon system. A day on Earth will equal a month. Both will have the same duration. Earth and Moon will face each other perpetually, like two dancers frozen in mid-step, staring into each other's eyes for eternity. But how long will this take? And what will the system look like when it reaches this state? The calculations are complex because the recession rate changes over time as the distance increases and Earth's rotation slows. But various analyses suggest that double tidal locking, if nothing else interferes, would occur in roughly 50 billion years. That is an almost incomprehensible span of time. For comparison, the universe itself is only about 13.8 billion years old. The Sun formed about 4.6 billion years ago. The Sun will exhaust its hydrogen fuel and begin to die in about 5 billion years. 50 billion years is roughly 10 times the remaining lifetime of the Sun. This means that the Earth-Moon system will never actually reach double tidal locking through the gradual process we have been describing. Long before 50 billion years pass, the Sun will have evolved through its death throes, and that evolution will dramatically and irreversibly alter the Earth-Moon system. In about 5 billion years, the Sun will begin to run out of hydrogen fuel in its core. For the past 4.5 billion years, and for the next 5 billion, the Sun has been and will continue to be a main sequence star, steadily fusing hydrogen into helium in its core. This process releases enormous amounts of energy, which is why the Sun shines. But hydrogen is a finite resource. Eventually it will run low. When the hydrogen in the Sun's core is depleted, fusion will cease in the core and begin in a shell surrounding it. The core itself will contract and heat up while the outer layers of the Sun expand dramatically. The Sun will swell into what astronomers call a red giant, growing to perhaps 200 times its current radius. Its outer edge will expand beyond the current orbit of Mercury, beyond Venus, and possibly reaching or even exceeding the current orbit of Earth. Whether Earth survives this expansion is uncertain. The Sun will lose significant mass as it expands, shedding material into space through an increasingly powerful stellar wind. When a star loses mass, the gravitational pull on its planets weakens and the planet's orbits expand outward. Earth's orbit might move far enough out to escape being engulfed by the swelling sun, or it might not. The calculations are sensitive to details that we cannot precisely predict. Even if Earth survives by moving to a wider orbit, it will not survive in any recognizable form. The heat from the nearby bloated sun will be immense. The oceans will boil away. The atmosphere will be stripped off. The surface will be heated to thousands of degrees. Earth will become a charred, sterile rock, any trace of its watery living past erased by the relentless radiation from the dying sun. The moon will experience similar devastation. It too will be heated intensely. Any volatiles that might remain frozen in shadowed craters at its poles will vaporize. The surface will be transformed by the extreme heat. Both Earth and Moon will be transformed into scorched, dead worlds orbiting the remnant of a dying star. After its red giant phase, the Sun will shed its outer layers entirely, creating a planetary nebula, a beautiful shell of glowing gas expanding into space. What remains will be the Sun's core, now exposed, a dense object about the size of Earth, but containing most of the Sun's original mass. This remnant is called a white dwarf. A white dwarf produces no energy through fusion. It simply radiates away the heat it accumulated during its earlier life. Over billions of years, it will slowly cool and dim. The white dwarf sun will provide almost no light or heat to whatever remains of the solar system. Any planets that survive will be frozen, dark, orbiting a fading ember in the vastness of space. If Earth and Moon survive the Sun's red giant phase, they might continue their tidal evolution in this transformed environment. The tidal interactions would continue to operate, gradually bringing the system closer to double tidal locking. But the timescales are so long and the conditions so different from today that making detailed predictions seems almost meaningless. Let us set aside the Sun's evolution for a moment and consider what the Earth-Moon system would be like if it could reach double tidal locking without interference. This thought experiment helps us understand the end state toward which the system is evolving, even if external factors will prevent it from ever being reached. In the tidally locked state, a day on Earth would equal a month. The Moon would orbit Earth once while Earth rotated once. But how long would this day-month be? When Earth's rotation slows to match the Moon's orbital period, the Moon will be farther away than it is now. The recession will have continued until the system reaches equilibrium. Calculations suggest that at equilibrium, the Moon would be at a distance of about 550,000 kilometers, roughly 44% farther than its current distance. At this distance, the orbital period, and therefore the length of both the day and the month, would be about 47 of our current 24-hour days. Imagine living on a world where a single day lasted 47 times longer than it does now. The sun would crawl across the sky with agonizing slowness. It would take nearly 24 of our current days for the sun to move from the eastern horizon to directly overhead. Another 24 current days would pass as it descended toward the western horizon. The daylight portion of each day would last about 23 and a half of our current days. The night would be equally long. The temperature extremes would be enormous. The daytime side of Earth would heat up for weeks under continuous sunlight. Without the rapid cycling of day and night that we experience now, heat would accumulate. Surface temperatures on the day side would climb far higher than they do today. The night side, conversely, would cool for weeks in continuous darkness. Temperatures would plunge far lower than any nighttime temperatures we experience. The difference between daytime and nighttime temperatures would be vastly greater than anything in our current experience. Today, the day-night temperature difference at most locations is perhaps 20 or 30 degrees Celsius. On a tidally locked Earth with 47-day-long days, the temperature difference might be hundreds of degrees. The day side might bake while the night side freezes. This would make the planet largely uninhabitable, at least for life as we know it. The extreme temperature swings would exceed what most organisms could tolerate. Plants could not survive weeks of darkness followed by weeks of intense sunlight. Animals could not endure the extreme heat and cold. Only the regions near the boundary between day and night, the terminator zone where the sun hangs perpetually near the horizon, might maintain moderate enough temperatures for life to survive. But wait, there is more complexity to consider. In the tidally locked state, the moon would hang motionless in the sky for observers on one hemisphere of Earth. It would never rise or set. It would never move across the sky. It would simply hang there, fixed in one position, forever. The hemisphere of Earth facing the moon would see it always, day and night, never moving. The hemisphere facing away from the moon would never see it at all. For half of Earth's surface, the moon would be a permanent feature of the sky. For the other half, it would be forever invisible. The tides would be locked in place as well. The tidal bulges would no longer sweep around Earth as the planet rotates. They would remain fixed, always pointing toward and away from the moon. There would be no tidal cycles as we know them. The ocean level at any given location would be permanently higher or lower, depending on its position relative to the moon. Coastal regions directly beneath the moon or on the opposite side of Earth would have permanently elevated water levels. Regions 90 degrees away would have permanently depressed levels. This is such a different world from what we know that it is. Difficult to imagine. The rhythms that define life on Earth, the daily cycle of light and dark, the monthly cycle of lunar phases, the twice-daily cycle of tides, all of them would be radically altered or eliminated entirely. The 47-day rotation period would replace the 24-hour day as the fundamental rhythm of the planet. Everything would be different. But as I said, this will not happen because the sun's evolution will intervene long before Earth's rotation slows enough to achieve tidal locking. The end state we have been describing is a theoretical limit, not a practical prediction. Let us think about more realistic timescales. What will happen to the Earth-Moon system over the next million years? The next 100 million? The next billion? In 1 million years, the moon will be roughly 38 meters farther away than it is now. That is about 38 meters in a distance of 384,000 kilometers. The change is utterly negligible. Days will be about 14 milliseconds longer. The tides will be imperceptibly weaker. The moon will appear fractionally smaller in the sky, but no human eye could detect the difference. For all practical purposes, the Earth-Moon system in 1 million years will be identical to the Earth-Moon system today. In 100 million years, the moon will be roughly 3,800 kilometers farther away, about 1% of its current distance. Days will be about 1.4 seconds longer. The tides will be about 3% weaker. The moon will appear about 1% smaller. These are measurable changes, but still not dramatic ones. An observer transported from today to 100 million years in the future would notice little difference in the moon or the tides. In 500 million years, the moon will be roughly 19,000 kilometers farther away, about 5% of its current distance. Days will be about 7 seconds longer. The tides will be about 14% weaker. Total solar eclipses might become noticeably different because the moon will appear smaller relative to the sun. The balance between the angular sizes of moon and sun that gives us our current eclipses will shift. In 1 billion years, the moon will be roughly 38,000 kilometers farther away, about 10% of its current distance. Days will be about 14 seconds longer. The tides will be about 27% weaker. The moon will appear noticeably smaller in the sky. Total solar eclipses may become impossible because the moon's apparent size will be too small to completely cover the sun. Instead of total eclipses, we will have only annular eclipses, where a ring of sunlight remains visible around the moon's silhouette. This transition from total to annular eclipses is actually a significant astronomical milestone. Total solar eclipses are possible today because of a remarkable coincidence. The sun is about 400 times larger than the moon in diameter, but the sun is also about 400 times farther away. These two factors almost exactly cancel, making the sun and moon appear nearly the same size in our sky. This coincidence allows the moon to just barely cover the sun during a total eclipse. But this coincidence is temporary. It is a product of where we happen to be in the long evolution of the Earth-Moon system. In the distant past, when the moon was closer, it appeared much larger than the sun. Total eclipses were not just possible but easy. The moon could cover the sun with room to spare. In the distant future, when the moon is farther away, it will appear smaller than the sun. Total eclipses will become impossible. We live in a special time, a window of cosmic history during which the geometry allows for total solar eclipses. In 5 billion years, as the sun approaches its red giant phase, the moon will be perhaps 150,000 kilometers farther away, roughly 40% of its current distance. But by this time, the sun will be swelling, its surface expanding toward Earth. The concerns about eclipses and tides will be irrelevant. Earth's oceans will have boiled away. The atmosphere will have been stripped into space. Whatever remains of Earth will be a scorched rock orbiting too close to a dying star. The future of the Earth-Moon system is thus intertwined with the future of the Sun. We cannot talk about the long-term evolution of Earth and Moon without considering the star that dominates our solar system. The tidal evolution that has been proceeding for 4.5 billion years will continue for another 5 billion, but then everything will change. There is another factor worth considering in the distant future. The sun's luminosity is slowly increasing even now, during its stable main sequence phase. As hydrogen accumulates as helium in the sun's core, the core gradually contracts and heats up, causing the fusion rate to increase. The sun today is about 30% brighter than it was when Earth formed 4.5 billion years ago. This increasing luminosity will eventually make Earth's surface too hot for liquid water. In about 1 billion years, the sun will be bright enough that Earth's oceans will begin to evaporate more rapidly than the water cycle can return moisture to the surface. The planet will enter a moist greenhouse state, with water vapor accumulating in the upper atmosphere where it can be broken apart by ultraviolet radiation. The hydrogen will escape to space while the oxygen remains behind. In about 2 billion years, Earth may lose its oceans entirely. The surface will become a dry, hot desert, perhaps similar to Venus today. Without oceans, tidal dissipation on Earth will change dramatically. The tides in the solid Earth will continue, but they will be much less efficient at dissipating energy than ocean tides are. The moon's recession rate will decrease significantly, so the future evolution of the Earth-Moon system depends on factors far beyond just the tidal physics. It depends on the sun's evolution, on Earth's climate, on whether oceans exist to dissipate tidal energy. All of these factors are interconnected, creating a complex web of cause and effect that extends billions of years into the future. Let us bring this back to human timescales for a moment. What does the moon's recession mean for us, for human civilization, for the foreseeable future of our species? In practical terms, almost nothing. The changes are far too slow to affect anyone alive today, or anyone who will live for thousands or even millions of years. 3.8 centimeters per year is completely imperceptible on human timescales. The moon you see tonight is essentially identical to the moon that your great-great-grandparents saw. It is essentially identical to the moon that Julius Caesar saw, that the builders of the pyramids saw, that the first humans saw when they looked up at the African sky hundreds of thousands of years ago. The moon has been a constant presence throughout all of human history. It has been our companion since before we were human. It has marked the passage of time with its phases. It has lit our nights with its reflected sunlight. It has inspired myths and legends and poetry and science. And it will continue to do so for as long as humans exist, because the changes are simply too slow to matter on any timescale relevant to human civilization. But the knowledge that the moon is moving away does change our perspective. It reminds us that the cosmos is not static. The Earth-Moon system that seems so permanent, so fundamental to our existence, is actually slowly evolving. The moon is leaving us, and has been leaving us since before life began on Earth. This connects the tides you see at the beach to processes that operate on timescales of billions of years. Every tide is part of the mechanism that is pushing the moon away. Every wave that breaks on a shore is dissipating energy that ultimately comes from Earth's rotation. The familiar rhythm of the tides is linked to cosmic evolution on the grander scales. There's something profound in this realization. The physics that explains why the moon is receding also explains the tides you experience every day. The same mechanism that has been operating for 4.5 billion years continues to operate every moment. You are living inside a cosmic engine, a system that is slowly transferring angular momentum from Earth to moon, gradually changing the relationship between our planet and its companion. The moon has been Earth's partner for 4.5 billion years. It formed in violence, in the aftermath of a collision that nearly destroyed our planet. It has been drifting slowly away ever since, pushed by tidal forces that connect the oceans of Earth to the orbit of the moon. It has stabilized Earth's axial tilt, making our seasons predictable. It has raised tides that may have been important for the origin of life. It has lit our nights and marked our calendars and inspired our imaginations. And now we understand why it is leaving. We understand the physics of tidal interactions, the transfer of angular momentum, the slow unwinding of the Earth-Moon system. We can measure the recession with extraordinary precision, tracking the moon's position to within millimeters using lasers bounced off reflectors left by astronauts half a century ago. This understanding is itself a remarkable achievement. For most of human history, the moon was mysterious. Its motions were tracked and predicted, but not understood. Its connection to the tides was suspected, but not proven. Its origin was unknown. Its future was unimaginable. Now we know that the moon formed from the debris of a giant impact. We know that it has been receding throughout Earth's history. We know that it will continue to recede for billions of years more. We know that eventually, the sun's death will transform both Earth and moon beyond recognition. We've traced the story from beginning to end, from the fires of formation to the cold darkness of the far future. The moon is leaving us. This is not tragedy. This is not cause for alarm. It is simply the way the universe works. Physics operates according to its laws, indifferent to human concerns. The same gravity that holds us to Earth's surface is slowly pushing the moon away. The same tides that fishermen and surfers and sailors have learned to read are the mechanism of the moon's departure. There is beauty in this understanding. The universe operates according to principles we can discover and comprehend. The motion of the moon, which once seemed governed by gods or magic, turns out to be governed by physics. Gravity, angular momentum, tidal friction, these part concepts allow us to understand not just what is happening, but why. The moon you see tonight is 3.8 centimeters farther away than it was a year ago. It is about 3 meters farther away than it was when you were born. It is about 150 meters farther away than it was when the first humans looked up at the night sky. These distances are tiny, imperceptible, meaningless on human scales, but they add up over millions of years, over billions of years. The moon that our ancient ancestors saw was measurably closer than the moon we see tonight. The moon that our descendants will see, if humanity survives that long, will be measurably farther. The dance of Earth and Moon continues. It has been going on for 4.5 billion years. It will continue for billions more. The music slows over time as Earth's rotation decreases and the moon drifts outward. But the dance does not stop. It will not stop until the sun dies, until external forces intervene, until the system is transformed beyond recognition. And through it all, the moon will continue to illuminate Earth's nights. Slightly smaller each passing eon, slightly farther away, but still there, still raising tides, still stabilizing Earth's axis, still watching over the planet where life arose and intelligence evolved and beings emerged who could look up at the sky and wonder why their companion was slowly drifting away. The answer we now know lies in the tides, in the bulges of water raised by the moon's gravity, in the friction between ocean and ocean floor, in the offset between where the bulge is and where it should be, in the torques that transfer angular momentum from Earth's spin to the moon's orbit. The tides are pushing the moon away, every tide, every day. For billions of years past and billions of years to come, the moon is leaving us, slowly, imperceptibly, inexorably. And in its departure, we see the universe operating as it always does, according to laws that are elegant, understandable, and ultimately indifferent to human hopes and fears. The moon is leaving us at 3.8 centimeters per year. This is what physics demands. This is what the universe dictates. And this is what will continue until forces beyond the tides intervene to write the final chapters of the Earth-Moon story. Look up at the moon tonight. Know that it is slightly farther away than it was last year. Know that every tide you have ever witnessed has contributed to its departure. Know that the same physics connecting Earth and Moon connects worlds throughout the cosmos. And know that in understanding why the Moon is leaving, we have gained something precious. A glimpse into the workings of the universe, a connection to processes that span billions of years, a perspective that places our brief human lives within the vast sweep of cosmic time. The Moon is leaving us, but it is leaving slowly. And tonight, it is still there, still beautiful, still ours to wonder at. That is enough. That is more than enough. That is everything.